Welcome back, everybody. AP Chemistry, Unit 5. This is Section 4, where we're going to build off of those voltaic cells that we were working with, finding our energy potential, and working with something called the Nernst equation. And the reason we want to take a look at this is because we've only worked with standard voltages to this point, which means that we have solutions that are 1 molar in strength, and that there is 1 atmosphere of pressure working on the system. The reality is we're almost never in those conditions. So we want to take a look at what happens when the concentrations change because that will affect our voltage, and that's what the Nernst equation takes into account. So the direction in which the voltage will shift, we can predict those numbers when you realize that cell voltage is directly related to that spontaneity. In other words, if we take a look, we see that voltage will increase when we add the stronger reactants in there, or we have more product that we can make, or if I can take some of that out of the system. But as we make more and more product in there, the reactant will decrease, and that will actually affect my voltage as well. So my battery will start to kind of putter out, and you always hear in the wintertime they always have ads for, taking the strength of your acids of your car battery to winterize your battery. That's what they're doing. They're taking a look at what is the strength or the concentration. So after time, we know that voltage will drop and become zero as this redox reaction reaches equilibrium and just kind of stops. Okay, so let's take a look at how this works. And there's a couple of different equations we can work with. Some of you are going to prefer working with the log of this. Some of you are going to prefer to keep working with the natural log of Q as we go. But notice that we've got a couple of things that are different that should catch your eye. First of all, here is that E value that we've been capturing, the potential energy. Okay, that's in the perfect world scenario. And when we're using the Nernst equation, we're taking a look at cell voltage that's in the real world, okay, when we're taking into account different things. You'll notice that in the last section, we're dealing with K values. And so I said that if we have a reaction of A plus B, there's my reactants, there's my product, we could determine my equilibrium point by just taking my C strength or concentration times or divided by, I should say, the product of my reactants. Okay, and I just take a look at those strengths, that would give me my K. If I have a large K, then I would find that the reaction would actually be spontaneous. But Q then would take into account something just a little bit more indicative. And let's say, for example, I have A plus B yields 2C. How Q is different, these two are so similar to one another in concept. How Q is different is it does take a look at the concentration, but it also takes a look at those at the number of times that will produce. In other words, the coefficients. And so I take a look at my C value times my A and my B value and my strengths. Because the coefficient here is 1, I would just have to the 1 power. Okay, so that's how this all works within that type of example. Okay, now I see that my Q is accounted for, my my potential and energy is accounted for. We know how to do that. Just be aware that if you're going to use logarithm functions versus natural log, your constant is going to be a little bit different, okay? And will still be the number of electrons that are involved and so on. So let's consider a voltaic cell in which the following reaction occurs. Okay, we have oxygen plus hydrogen ions will make bromide and water and bromine gas. Now, for this, we want to see a couple of things because we've got a couple of things that we've got to be aware of. Now, first of all, if I take a look, this is a +1, -1, all this fun stuff. We know how to do this, which is important because we got to see who's oxidized, who's reduced. But also, when I'm taking a look at my Q value, or my strengths, I should say, with these concentrations, when I'm talking about gases and liquids, my strength number will just be A1. And that's because it's not really interacting with anything. There are no ions that are being freed up. Okay, so just kind of a qualifier at the beginning of things. Let's take a look, first of all, at this equation, and let's find out what's going on. We see that from this, that the reduction end of things, that's going to be my oxygen that's going to be reduced. I find that I have, in my balanced equation, I have 4 electrons, and I have 4 hydrogens, and I end up with oxygen, and that will give me water. And so looking at my equation with oxygen and water, I see that I end up with a on this one, I see a 1.23. Okay, I'm going to use actually a voltage of 1.229. Okay, and that's, again, you use your 1.23, that's fine. 1.229 is what I'm going to use. Now, oxidation, that's going to be my bromine then. I'm going to end up with 4 bromides and that will involve 2 bromine gases and 4 electrons. I end up with a value on this one of negative 1.077 volts. And the reason it's negative 1.077, here you see 1.09, but it's not being reduced, it's being oxidized. So I have to put a negative out in front. So my E value, if I was going to take a look at that, my E value or my change in that is going to be a plus 1.5, or sorry, 0.152 volts. Okay, so now I've got my components of this. I found my E value. Now let's go ahead and do all of these things. Again, the goal is to get my my real world energy value in here. So let's find my Q. Okay, if I'm going to be using this equation, I've got this as a 0.152 volts. Okay, that's done. Now let's find my Q value. All right, so my Q ends up being, looking at my equation, I see that I've got water and bromine. Okay, so it's water, and notice that the coefficient is a 2, and I have my bromine. And once again, my coefficient is a 2. Since those are liquids in this case, that value, that strength, that concentration, they all mean the same thing, that's all going to be a 1. Now, I take a look at the denominator end, that's going to be my reactants end. Okay, so that's oxygen, that's a gas, and that coefficient is a 1. And since it's a gas, I give a value of 1. Now, I take a look at my hydrogen ion, and that's raised to the 4th power. But the problem tells me that my concentration is a 0.1 molar. And then lastly, I have the bromine itself. And let's see, the bromine itself is the bromide ion, and that strength is again a 0.1. And notice that I've got a coefficient of 4. And I realized that I just made a mistake because I said that that's a 1. That's a 1 because it's a 1 atmosphere, not a 1 because of the dissociation. So the pressure of that was my mistake in speaking, but we just kind of plug in those values because they gave me 1 atmosphere pressure. Remember, the Nernst equation does take a look at how pressure will affect the system. In fact, there's 1 for the atmosphere, so we are under standard conditions. Okay, so if I plug in those values, I end up with my Q value. Then, again, if I just plug in all of these things, I just multiply straight across, I end up with a Q value in all of this. Let's see, what did I end up calculating it out to be? Of 1 times 10 to the 8th. Okay, so again, it's just plug and chug, plug your numbers in there, you should be fine. Now let's use the Nernst equation because this ended up being 1 times 10 to the 8th. All right, so doing all of that, 0.152 minus this. Now remember, my number of moles involved was going to be a 4, and so I can just take a look, and this times the log of 1 times 10 to the 8th divided by 4, subtract, I end up with an E value in this case of being a negative 0.082022. Okay, so yeah, basically just kind of take a look. To double check, the log of 1 times 10 to the 8th ended up being 18.4, and so I just kind of multiply those numbers in there, and that's how I get this value. Okay, so pretty straightforward with it. Just kind of keep track of your algebra along the way, and you should be fine. Now let's take a look at another example on this, and we're going to be taking a look at this time. We're going to be taking a look at hydrogen peroxide. Now be careful. Hydrogen peroxide, O2 with a -2 charge, is peroxide. And so in this case, I only have one of those. And so this particular one, because it is peroxide, my oxygen has a -1 charge. My hydrogen is a +1. And this is a +1, this is a 0, this is a +3, -2, and +1. Okay, so it's a little bit different because it's peroxide. We've got to do a couple of trickier things. So let's go ahead and set up our balanced net ionic equation, and we can do a couple of things with all of this. In fact, let me take a look at what the questions are going to be with this. And let's see, there we go. And we can calculate all of these values. All right, so I said this was a -1, +1, a +1, 0, +3, -2, +1. Okay, now I can see all the components. I want to calculate for my E value. Okay, calculate for the E value. Well, I've got to do some other things, don't I? My E value does depend upon my redox reaction. And so what's getting reduced in this case ends up being my peroxide. And so I end up going 3 of my peroxides, O2, um, and hydrogen ion, and 2 electrons. That will give me 2 waters. And I end up using my chart. I see that the reduction potential is going to be a 1.763 volts. Now remember, it's 3, so actually there ends up being 6 electrons involved. My oxidation numbers then, again, from my charts, I see that I have 2 golds, and that's going to give me gold plus 3 on there. And I've got to multiply that in front of everything, and I end up with a potential of negative 1.498 volts. So my E value then, my potential, is a 0.265 volts. Okay, so I've got my E. Okay, that ended up being just double checking my numbers, a 0.265 volts. Okay, now let's write the Nernst equation. And you're going to find this on the AP exam quite a bit. You don't have to do math with it. They do want to make sure that you know how to set up the equation, though. Okay, so a Nernst equation with this is simply saying we have my E value, and we found my potential is going to be 0.265 volts minus the natural log of my gold ion, and it is squared. And the reason is I have this out in front. I see that I have my hydrogen peroxide. And notice with that one, it is cubed. And lastly, I have my hydrogen ion, but there was already a 2 in front, and so my hydrogen ion ends up being to the 6th power. Okay, so we just set up those things, those equations with this. And so what did I do? This is my Q value, isn't it? My Q value is basically that if I just plug it in. Okay, so I had a negative 0.265. What did I forget in here? I forgot to include the constant of a 0.0257 divided by the number of electrons in there. Okay, so make sure we've got those pieces in there and we're ready to go. Now the third part is saying, okay, when we have these conditions, we have my strength, I have my strength, and I have my strength. I have 3 strengths that I include in there. So if I know my equation, I see that my gold strength was a 0.250 molar. I see that my hydrogen was a 1.25 molar, and that my peroxide was a 1.5 molar. Okay, so now let me clean it all up. And so we wrote the equation in there, and I forgot to include because I just was overlooking things. But my E value then is going to be a is going to be a 0.265 volts minus the 0.0257 constant over 6 electrons involved times the natural log of my gold. Okay, and that ended up being a 0.250, and that was squared, over my 1.50 to the 3rd power. Okay, that was cubed, that was my water. And lastly, I have my 1.25 to the 6th power, which was, let's see, I'm just double checking everything. Yep, and so that would be my hydrogen ion concentration. Okay, so if I do my math, I'm just going to do this, that the natural log of a 0.0625 over a 3.4, okay, so I'm just doing this component right here, times a 3.8, that ends up being a negative 5.33. Okay, so I just kind of derived this for you. Now we can get a negative 5.33. Okay, so that's all my Q value right there, done. And so now I can clean this all up, and I end up with a 0.265 minus the 0.0257 over 6 times the negative 5.33. Okay, if I do all that, I end up with a value of 0.288 volts. Okay, so hopefully you didn't get lost in what I was doing here. I was trying to say that this will equal this, this will equal this, this will equal this. So this is how I got, and I took the natural log to get a negative 5.33. Then I take that times this and then subtract along the way. Okay, so that's how I got those values. All right, so that being said, with all of this, okay, again, just keep track of your math. We can do this to figure out probably the most important aspect of it all. We can use this equation in the experimental determination to figure out the strengths of ions in solution. Again, I said that within winterizing your battery and that kind of thing, we can figure out how strong they are. And suppose we measure the cell voltage and know all but one of the species in the two half cells. Then it should be possible to calculate. Okay, so let's take a look at what that looks like. If we have this reaction of zinc in there, and we found that my real life energy is going to be 0.560 volts. It's found that the voltage is 0.560 volts when we have a strength of my zinc ion, and the pressure of my hydrogen is going to end up being 1.0 atmospheres. What was the strength of that in the hydrogen to hydrogen ion half cell? Okay, so to do this type of problem, we want to do a couple of things. Now, first of all, we need to kind of work backwards with things. Oops, I just changed that. I want to change it right back to this. All right, so we're going to do a couple of things. Now, first of all, let's find my potential energy, and we want to find how many electrons are involved in this. In other words, what do you know? We have to do a redox reaction. Okay, so when we do this, we see that being reduced, we have my two hydrogen ions, and I have two electrons that are involved in that, and I want to find my hydrogen gas. And remember, that would be a oxidation of 0. All right, so then we get to my zinc. That is a solid as well, so it's going from a 0 to a +2. So that would involve 2 electrons as well. All right, so I know how many electrons are in there, and I know that this guy is going to be 0.00 volts. And I look, and again, I'm just using my chart, so that's how I know that. I have a 0.762 volts with my zinc. So what's the difference in here? My potential energy ends up being a 0.762 volts. My N value I found to be 2 electrons. Okay, so now I can just go ahead and plug and chug. I see with my Nernst equation, remember that's going to be E equals my potential E over my concentration, and I'm going to use 0.0257 volts over my N times the natural log of Q. All right, so I know all of my pieces in here, and I'm just basically going to be solving for Q, aren't I? So I have my 0.560 is my E value. My potential energy we found to be a 0.762 volts minus the 0.0257 over my electrons involved, and there were 2 electrons involved, times the natural log of Q. So when I go Q by itself, I take the inverse, and notice though, I can actually find out something a little bit more about this from my balanced equation. So before I find Q, let's do this. Let's take a look at 0.560. That equals 0.762 minus 0.0257 over 2 times the natural log. And remember we were doing in the last slide, we were actually just setting up the Nernst equation, setting up those things. So I see that I had my pressure of my hydrogen, and so I had the hydrogen gas, and the balanced equation, that was a 1. And I see also I have my zinc in there, and that's my zinc ion. Okay, so there's a couple things in my products, and I see that was a 1 as well, wasn't it? Now I see also in the product side, I have my hydrogen ion, and that coefficient was a 2, and I have my zinc metal, and that concentration, or that multiplier is a 1. So I see that piece in there, but remember, my zinc is a solid, and so that's just a 1 when it's a solid in there. A solid or a liquid ends up being a 1 value for concentration. So essentially, I can cancel that out. So if I look at all of this and I just solve for this, I see that my hydrogen ion concentration equals a 4 times 10 to the negative 4. Okay, I multiply both sides by my hydrogen concentration. My hydrogen concentration is what we're looking for in this case. So that's my x squared. So x squared, and basically consolidate all this in. Then I take the natural log. I plug in my value of my 1 atmosphere here. I plug in my value of a 1 molar here. So it's the natural log of 1. And so basically just doing that math, you should end up with 4 times 10 to the negative 4th for that concentration. Now I know how strong that acid is in there, and now I know what basically the lifespan is left with my battery. Okay, so just following the steps of there, you should be okay. It's a little bit tricky in there, so watch your things, but you should be able to do problems 1 through 5 now. All right, good luck, guys.